And this is an infusion experiment, a very quick experiment of 2 minutes infusion using a LC TOF system with a whole mixture of compounds. And I picked the compound at a higher mass at about 840 as an example to show you what spectral accuracy can do above and beyond mass accuracy. So as you can see, for this high resolution data, the advantage is that the monoisotope peak here is well baseline resolved from the A+1. In addition, you also have high mass accuracy to start with. So we don't really need any external calibration now at this point to improve mass accuracy. So we'll go ahead and do a mass accuracy search for possible elemental composition first and see what we get, and see if we would be satisfied with the results first before we can see if spectral accuracy can be brought into play here. So a typical elemental composition determination page here, where we're not going to make it too complicated because mass is already too high. So we're going to limit ourselves to CHNOS, 5 possible elements. And we're going to search within ±4 ppm mass accuracy. It may be a little too generous, but we'll see later. And we can safely assume it's an even electron. And then we go ahead and do a elemental composition search within ±4 ppm mass accuracy tolerance window, and with only 5 possible elements. Well, we get a total of 90 possible formula candidates at 4 ppm mass tolerance window. And what's listed on this slide is the top 21 based on mass accuracy. So the smallest mass accuracy, mass error compound will be listed on top of the list, and the one with the largest mass error, close to 4 ppm, will be listed at the bottom of the list. Now, the top 20 candidates, its mass accuracy are within 1 ppm of the measured accurate mass, and the number 21 happens to be just outside of that 1 ppm window at 1.01 mass error. So had we been more aggressive in terms of setting our mass tolerance window, we might have taken a chance with 1 ppm mass tolerance and ended up with the top 20 to work with. But for now, we're going to live with 4 ppm mass tolerance window and with 90 possible formula candidates. And I want to use the 21st hit as an example, which is slightly outside of the 1 ppm mass tolerance window. On this next slide, you can see we have plotted the theoretically calculated mass spectral data and overlaid that on top of the actual measured mass spectral data. The red trace is the actual measured, the blue is the theoretically calculated mass spectral data. For this particular candidate, number 21, well, there's another difference is because the peak shape is mismatched. So we can't really judge whether this would be a contender, a possible formula candidate. And that's where we introduce the peak shape calibration and the concept of spectral accuracy into the play. Well, we go back to our slides. We copy the mass spectrum here. That's the raw data at A44, which is monoisotope mass at A44.5. And because it's a high-res data with the reasonable mass accuracy to start with, we are going to perform a mass spectral peak shape only calibration. We're not going to perform the mass calibration anymore. And the peak shape information comes from the monoisotope peak of this unknown itself. So it's a self-calibration process that doesn't require any other standards. The reason we can do that is that the monoisotope peak is isotopically pure. It doesn't have any isobars compounding the picture. And it provides a perfect line shape measurement for this particular instrument at this particular mass. So we can select the monoisotope peak itself as the peak shape standard to perform a calibration that will calibrate the peak shape function into something that's mathematically definable. And that calibration function looks very much like the calibration function we have seen before. The only difference is that it will preserve the mass location, so that whatever mass accuracy the original data comes with, it will be preserved. And that calibration, although it's derived or calculated from the molar isotope peak itself, we can safely apply that to the rest of the isotope clusters belonging to the same ion to convert the raw mass spectral data into a peak-shaped calibrated mass spectral data. And once that peak shape has been calibrated, now we can compare a possible formula by calculating its theoretical mass spectral data and overlaid it with the calibrated trace to see how close, how similar they are, and calculate the spectral accuracy measurement for this particular compound. And the candidate that provides the highest spectral accuracy, or with the smallest spectral error, is a most likely candidate for the unknown. And here, let's go back to our screenshot in the software, where we're going to look at the number 21 again. We calculated its theoretical mass spec, and we have also calibrated the actual mass spec into the same mathematically definable peak shape function. Now you can see number 21 actually looks quite plausible with almost perfect match between the theoretically calculated and the calibrated mass spectral data. Now if we, at this point, sort the whole list of 90 possible compounds based on spectral accuracy, we'll get the same list but with a different ranking. Number 21, with its mass accuracy slightly outside of the 1 ppm mass tolerance window, actually has a very high spectral accuracy of 99%, and it's the highest spectral accuracy hit, and that turned out to be the correct formula. Now, you might wonder, that's the number 1 hit, what the number 3 hit would look like. Are they going to be significantly different? Well, let's take a look at that. And this is the number 3 hit with 97% spectral accuracy. As you can see, there's a significant difference at this point on the A+1 peak. And the copper number is different. It's different enough, maybe it might only differ by 1%, in other words, but our software can pick that up in the form of a significant spectral accuracy difference. So instead of considering 90 possible formulas, we have narrowed it down to maybe the top 1 or top 2 through the use of spectral accuracy. There are other applications of spectral accuracy for high-resolution systems. For example, there's an application that was published in JAS by our customer, Dr. John Erb, on the application to thermal altitude orbit trap. And what he found was that for larger masses, for example, larger than 900 Dalton, he could eliminate up to 99% of the incorrect formulas from consideration, and significantly reducing the burden of formula determination.